Theory video 6. So I suppose that you have done the previous questions, and you understand all the details. If you have any questions, you must raise them. And if you haven't so far done the questions, you must do them before you go through this video. So now we developed an equation P equals 1 upon 3 Nm upon V average C squared. Then we can combine this equation with PV equals nRT. So what we can do is we can move this V here to the left hand side and take it as PV. Then once we do that, we know that it is going to be the same. Both sides, both the equations would have PV on the left hand side. Then we can equate these two equations. Then we get from the first equation here we move V to the other side, and then we get PV equals 1 upon 3 Nm average C squared. Then here already we have PV equals nRT. Then because both sides are PV, we can take 1 upon 3 Nm average C squared is equal to nRT. Right? So from this equation, we can get more further details about different combinations of values. Then we can use it to find out how the absolute temperature of a gas, that is a macroscopic property, is going to be related to the mass and speed of its molecules. The mass and speed of its molecules. So then if we take these quantities into consideration, we can take m into average speed squared is equal to 3 nRT upon n. Then we know capital N over n is going to be the Avogadro constant, that is the number of particles in 1 mole. Right? So you should remember how n and simple n they relate to. Then from there we can take m is m multiplied by average C squared is equal to 3 RT upon capital N A, Avogadro constant. Right? Then if you if we divide this by divide both sides by 2, right, then we get half m, that is mv squared. We are making it to mv squared, half mv squared, the kinetic energy equation, because C stands for the average speed. So that is the kinetic energy equation we can obtain from this. Half m average of C squared is equal to 3 RT upon 2 Na. Then again we discussed earlier that R upon Na is Boltzmann constant and has a value of 1.38 into 10 to the power minus 23 joules per Kelvin. Then we get kinetic energy is equal to half m C squared, O, which is going to be equal to 3 upon 2 kT. K is Boltzmann constant. T is the temperature in Kelvin scale. Right? So this equation is yet another thing that you need to understand. Right? So the thermodynamic temperature is proportional to the average kinetic energy of a molecule is an understanding that we need to get. The key equation here is going to be K, Boltzmann constant, is equal to R upon Na. Right? So you have to remember from where R is going to come. Right? So that comes from PV equals nRT. Then Boltzmann constant multiplied by Avogadro constant would give you R. That is another connection that you can figure out. So the mean transitional kinetic energy of an atom or a molecule is not transitional, I apologize, the mean translational kinetic energy. That is the kinetic energy that has the ability of conversion is proportional to the thermodynamic temperature. Right? So that means the higher the thermodynamic temperature, higher is the kinetic energy, and that is a relationship that we have already discussed. Then mean translational kinetic energy of an atom is proportional to T. Then this translational kinetic energy is received by a particle because it is moving in space from one point to another. Right? It is moving from one point to another. Due to this movement, it has a translational kinetic energy. That is the kinetic energy that can be translated. Then when there is a molecule that is made up of two molecules, while they move from one place to another, they will also spin or tumble around its own axis. That is known as rotational kinetic energy. So we have translational kinetic energy that is going from one place to another, and then rotational kinetic energy. So we have to understand the difference between these two. Translational kinetic energy, when you go to university levels, you will figure out that translational kinetic energy is what is being transferred. But rotational kinetic energy is going to be related to the self. Then we talk about the mean kinetic energy. We have to find the average kinetic energy of a molecule of gas. So what we do is we find all the kinetic energies of the individual molecules and then take the average kinetic energy of per molecule. Then if we take a single molecule and consider its movement throughout a prolonged period of time, from that also we can take the average kinetic energy. So whatever the means by which we obtain the average kinetic energy, it is going to be the same value. Then Boltzmann constant is a very important principle in physics because it actually tells us how microscopic particles relate or provide the macroscopic properties of a gas. That is how these particles, behavior of singular particles, give out properties such as temperature. Right? So now when we take the units of Boltzmann constant, we get joules per Kelvin, which is very small, 1.38 into 10 to the power minus 23 joules per Kelvin. Because when the kinetic energy increase is considered for each Kelvin increase in temperature, the kinetic energy of a molecule is going to be comparatively very low. Right? Then when we take that combination, we can understand why and how these microscopic properties such as the kinetic energy of a single molecule will affect the kinetic energy or the average kinetic energy, that is the temperature of which is a macroscopic property, how they are affected. So then we get another equation the average kinetic energy of a molecule is 3 upon T kT, 3 upon 2 kT, right? 3 upon 2 kT. So that is another, this is the third equation you have to remember from here. So the three equations are Boltzmann constant K equals R upon Na. Then kinetic energy of a molecule is equal to 3 upon 2 kT. And then we obtained this equation, this relationship, mean translational kinetic energy of an atom is proportional to T. So now they would give you questions. Now if you look at the 15, 16 and 17 questions you will have to do. If you find it difficult, please ask me. You have to just apply the equations and the details that they have provided. Now I'm going to just give you a tip on how to do these type of questions. When you consider question number 15, the Boltzmann constant K is equal to R upon Na. From values of R and Na show that K has a value of 1.38 into 10 to the power minus 23 joules per Kelvin. So you have to remember the values of R and Na, that is the gas constant and the Avogadro's constant. So when you remember these things, it is going to be really easy for you. Right, then we come to root mean square speed. That is the c squared, mean square speed c squared we have obtained in the earlier relationships. Now we need to figure out how it compares with c, that is the average speed. The exact relationship is taken by this connection. Now how these particles or the molecules with different speeds are distributed will give out the relationship. When we take that into consideration, we get the equation, the average speed is equal to root mean square speed. Root mean square speed, this is the equation that comes from that. Then the explanation is this. If you imagine three molecules with speed 10, 20 and 30 meters per second, right? Now this is, you can remember we discussed about very high speeds for molecules, right? Then how we get that is speed is equal to 10 plus 20 plus 30 divided by 3 because there are 3 molecules, then we get 20 meters per second. Then their square speeds are 10 squared, 20 squared and 30 squared. So their mean square speed is equal to 10 squared, 20 squared, 30 squared divided by 3. I hope you understood that, right? Then we get 467 meters squared per second squared. So then what happens is, when we get the square root of it, we get 22. But that is not going to be the same as the mean speed, right? So in the earlier equation, we said that it is going to be equal to, here we said in this equation average speed, mean speed is going to be equal to mean square speed. So now let's figure out what this is all about. The mean square speed of, that is the c squared, 467 meters squared s minus 2, is not the same as the square of the mean of the speeds in the example, right? They are not the same because 20 squared is 400, right? When we consider in general, what happens is the mean speed is equal to the root mean square speed. right? They are, in principle, they are similar. But because they are not the same, they are not the same, we take another value, root mean square speed, right? Root mean square speed, we define it as CRMS. CRMS is equal to root mean square speed. So this equation is another thing that you need to understand, right? So in the example, the three molecules would have CRMS 22 ms minus 1, right? So CRMS is equal to C squared and you take the square root, which is going to be different from the mean speed that we calculated, right? So if we square the mean speed, then we get 400. 400 square root is 20, but that is not the same as root mean square speed. I hope that makes sense to you. If you don't understand, please tell me this. Then I will explain it further. Do question number 18 and 19, then you would be able to understand it more. Then mass, kinetic energy and temperature. Now we realize that mean kinetic energy is proportional to temperature in Kelvin scale. So that means if we double the thermodynamic temperature of an ideal gas, that is from 300 Kelvin to 600 Kelvin, we double the mean kinetic energy, right? That doesn't really mean that we have double their speed. Why? Because Ke is proportional to V squared, right? V squared, kinetic energy is proportional to V squared. So that means we have increased the speed by a factor of root 2, right? So that is another connection, and this is something that they have asked you questions about. Air is a mixture of gases, right? You know that the air around us is mostly made up of nitrogen, but there are other gases in different proportions. Nitrogen, oxygen, carbon dioxide, etc. There are many gases in the atmosphere. The mean kinetic energy of nitrogen is going to be the same as that of oxygen and also of carbon dioxide. How is this? Because they repeatedly collide with one another. Nitrogen doesn't collide only with nitrogen, right? So they collide with oxygen, carbon dioxide, everything. So as a result, what happens is, this is gases that have been there in air for a long time. It is not something that is just released. So they share their energy, right? Carbon dioxide have a greater mass than oxygen, but because their kinetic energy, translational kinetic energy is the same, they move much more slowly than the oxygen molecules because of the mass difference. That is another important thing that you need to remember. If you go through all of this, if you have gone through all of the videos properly, you would be able to answer all of the questions in chapter questions. And after we discuss the reflection part, you would be able to do the end of chapters, right? So now here they have told you to make a list of the kinetic theory equations and what each term would mean, and also the values, right? So then you have to write your own proof to the main kinetic theory equation using the momentum change and Newton's laws. And whatever they have given here in this reflection part, you will have to do. When you do that, you will be able to answer all of the questions without any problem. So the summary is PV upon T is a constant. Then 1 mole of any substance contains Na particles. We call that the Avogadro constant, which has a value of 6.02 in 10 to the power 23. Then we got the equation of state for an ideal gas, PV equals nRT. Then we got PV equals capital nRT for n molecules. Then we have 4 assumptions that we made in kinetic theory. They move at random, colliding elastically with the walls. Volume means uh, the volume of a molecule is very small compared to the volume of the container. Then we assume that there are no forces of attraction between atoms in gases. Then the collision time is insignificant between the collisions. Then we deduce the relationship PV equals 1 upon 3 Nm average C squared. C squared is the mean square speed of the molecule. Then from that we got an equation, mean translational kinetic energy E equals half m c squared or 3 upon 2 kT. Then we got CRMS, the root mean square speed. It is the square root of the mean square speed of the molecule, and from that we ended our discussion. So now you will have to do these exam style questions. Whatever you find difficult, please ask me, and then I will discuss that in detail. Go through the book and the videos if you don't understand, and if you have questions, please ask them.